Students, so welcome back to my video lecture 2 on chemical bonding and molecular structure. So in the previous video I just started with octet rule. We learned the limitations of octet rule. We learned what is ionic bond, what are the characteristics of ionic bond, and what are the factors that favors the formation of ionic bond. And also we learned what is ionic bond, and we were talking about we learned the characteristic features of covalent bond, and we were talking about the factors that favor the formation of covalent bond, isn't it? Factors that favor the formation of covalent bond. I have discussed two factors. Which are those two factors? The combining atoms should have high ionization energy. So the atoms that are combining to form a covalent bond and to form a covalent compound, they should have high ionization energy, and the combining atoms should have comparable electronegativity. That means there should not be much electronegativity difference between the two atoms, the two combining atoms. So we have discussed these two factors that favors the formation of covalent bond. Then we have one more factor. We have two more factors which favors the formation of covalent bond. The third factor is the combining atoms should have comparable electron affinity. Electron affinity. The combining atoms should have comparable electron affinity. What do you mean by this? They both should be almost equally, they should have almost same electron affinity. They should have same or equal electron affinity or almost equal affinity. One thing, both the combining atoms should have high ionization enthalpy. One thing. The other one is they should have almost same electronegativity, or the next one is they should have almost same or equal electron affinity. The other one is the last factor that favors the formation of covalent bond is high effective nuclear charge. High effective nuclear charge. High effective nuclear charge, and shorter internuclear distance. Shorter internuclear distance. Shorter internuclear distance. Internuclear distance means bond length. The distance between the nuclei of the two atoms is called as bond length. So they should have shorter bond length and high effective nuclear charge. If they have high effective nuclear charge and shorter bond length, these are all the different factors that favors the formation of covalent bond. The combining atom should have high ionization enthalpy. The combining atom should have comparable electronegativity. The combining atom should have comparable electron affinity, and they should have high effective nuclear charge and shorter internuclear distance. Students, are we clear? Yes. Now, under ionic bond and covalent bond, we should learn a rule called as Fargen's rule. What rule is it? We should learn about what? Fargen's rule. Fargen's rule. Yes. Why do we need this Fargen's rule? In order to just know the covalent character in ionic bond. In ionic bond. See, ionic bond will have covalent character. A covalent bond will have ionic character. vice versa. Are you getting my point? Okay, remember this. Okay, an ionic bond is not completely ionic. An ionic bond will not be completely ionic. Okay, an ionic bond will have covalent character, and a covalent bond will have ionic character. Will have what? Ionic character. Please note these points. Okay, yes. So an ionic bond will have covalent character and a covalent bond will have ionic character. To what extent an ionic bond will have covalent character, and to what extent a covalent bond will have ionic character? This is explained by a rule, and what is that rule called as? Fargen's rule. What is that rule called as? Fargen's rule. Okay, to what extent, what is the percentage of covalent character in an ionic bond? What is the percentage of ionic character in covalent bond? This is explained by a rule, and what is that rule called as? The rule is called as Fargen's rule. Fargen's rule. Now, what according to Fargen's rule? Look here, simple, very simple. Okay, Fargen's rule says, okay, smaller the size of cation, and larger the size of anion, smaller the size of cation, larger the size of anion, more will be the covalent character. More will be the covalent character. More will be what? The covalent character. That's it, very simple. Okay, smaller the size of cation. Okay, obviously cations are smaller than anions, which we have learnt it in periodic table, isn't it? Now, smaller the size of cation, larger the size of anion, okay, more will be what? Covalent character in an ionic bond. More will be the covalent character in an ionic bond, and vice versa. Okay, vice versa means larger the size of cation, smaller the size of anion, more will be what? Ionic character. More will be ionic character. But remember, learn Fargen's rule this way. Smaller the size of cation and larger the size of anion, more will be the covalent character. Well, let me explain this with an example. Okay. Say I will take, okay, yes, sodium chloride, okay, yes, beryllium chloride and aluminium chloride. Okay, can you tell me which compound is more covalent? I have sodium chloride, I have beryllium chloride and aluminium chloride. You should tell me which compound has more ionic character. Which compound has, let me read the question, which compound has more covalent character? Okay, more covalent character. Okay, so you have to apply Fargen's rule. Which compound has more covalent character? So we have sodium chloride, we have beryllium chloride and we have aluminium chloride. Well, we know sodium chloride is formed by sodium ion and chloride ion, whereas beryllium chloride, we know it is formed by beryllium ion and chloride ion, whereas aluminium chloride is formed by aluminium ion and chloride ion. Okay, the anion is the same here, chloride, chloride, chloride. Okay, that means here the covalent character does not depend upon the size of anion, it depends upon the size of cation, because anion is fixed, chloride, chloride, chloride. So here we have to decide the covalent character based on the size of what? Cation. So we have sodium ion, beryllium ion and aluminium ion. We know that a cation with higher positive charge, okay, higher positive charge, okay, is smaller in size, isn't it? Okay, a cation with higher positive charge will be smaller in size, am I correct? So we have sodium ion, beryllium ion, okay, and aluminium ion. Okay, aluminium plus 3 charge, beryllium plus 2 charge, sodium plus charge. So higher the positive charge, smaller is the ion. So what is the order of ionic radii? Yes, aluminium ion is smaller than beryllium ion. Beryllium ion is smaller than what? Sodium ion. So this has least ionic size. Now what does Fargen's rule says? Smaller the size of cation, larger the size of anion, more will be the covalent character. Is that correct? So that means to say aluminium chloride is more covalent than beryllium chloride, which is more covalent than what? Sodium chloride. Am I correct? Aluminium chloride is more covalent than beryllium chloride, which is more covalent than sodium chloride. Smaller the size of cation, larger the size of anion, more will be the covalent character. Any doubts? Is that simple? Yes. I'll give you one more example for Fargen's rule. Let me quote one more example. Okay. So you should again tell me which compound has more covalent character. Which compound has more covalent character? Say I have lithium chloride, okay, sodium chloride, potassium chloride and cesium chloride. Okay, well, lithium chloride is formed by lithium ion and chloride ion. Sodium chloride is formed by sodium ion and chloride ion, isn't it? Potassium chloride is formed by potassium ions and chloride ion, and cesium chloride is formed by cesium ion and chloride ion. Here also the anion is fixed. Anion is fixed. Okay, isn't it? You cannot judge the covalent character based on the size of anion, because anion is the same in all the cases. But look at cations. All the cations have same charge, plus charge, plus, unipositive charge. But we know they belong to the same group. Lithium, sodium, potassium and cesium, they belong to the same group. We know as we go down the group, okay, ionic size increases. Ionic size increases. That means lithium is smaller than potassium, which is smaller than sodium, which is smaller than potassium. Potassium is smaller than cesium. Now therefore, which cation is smaller? Lithium ion is smaller. Therefore, smaller the size of cation, larger the size of anion, more will be the covalent character. So what is the order of covalent character in these molecules? Yeah, lithium chloride is more covalent than, okay, sodium chloride, which is more covalent than potassium chloride, which is more covalent than cesium chloride. Cesium chloride is, okay, highly ionic. Okay, it is highly ionic, whereas lithium chloride is a covalent compound. Lithium chloride is covalent compound. Okay, so lithium chloride is covalent compound, whereas cesium chloride is an ionic compound. Okay, is that simple? Okay, that's all about Fargen's rule. Please state Fargen's rule again. Smaller the size of cation, larger the size of anion, more will be the covalent character. Okay, well, no doubts in it. Fantastic. Okay, next concept. Yes, let us talk about the next type of bond. Okay, what is the next bond that I want to talk about? Yes, okay, I am talking about a next bond called as coordinate bond. Okay, it is called as coordinate bond, or it is also called as dative bond, or this is also called as electrocoordinate bond, electrovalent coordinate bond, anything is fine. Electrovalent coordinate bond. Are you getting, students? The third type of bond, Okay, what is this third type of bond called as? A coordinate bond, a dative bond, okay, a electrovalent bond. Electrovalent coordinate bond. If it is simply electrovalent, it's going to be electrovalent bond is also called as ionic bond, but it's not just electrovalent, it is electrovalent coordinate bond. Electrovalent coordinate bond. So students, what do you mean by coordinate bond or dative bond or electrovalent coordinate bond? Okay, see, hope you know about a covalent bond. If I consider covalent bond, for example HCl, we know I'm talking about covalent bond, don't just be confused. See, we know in covalent bond, each combining atoms will share one electron, isn't it? Here hydrogen will share one electron, chlorine will share one electron. So a covalent bond is formed by mutual sharing of electrons, isn't it? A covalent bond is formed by mutual sharing of electrons. Even hydrogen will share one electron, chlorine will share one electron. Okay, isn't it? Am I correct? So a covalent bond is formed by mutual sharing of electrons, but a coordinate bond, okay, is shared by, is formed by, it is the bond formed by okay, sharing of electrons. It is also formed by sharing of electrons, but okay, it is the bond formed by sharing of electrons by okay, one of the okay, the electrons are shared by one of the okay, combining atom, one of the combining atoms. Okay, so here in covalent bond, both the combining atoms will share electrons. Okay, in covalent bond, both the combining atoms will share electrons, but in coordinate bond, only one of the combining atom will share the electrons, the other one will not share the electrons. The other one is not going to share the electrons. Okay, only one of the combining atom will share the electron. For example, if I consider ammonium ion, in the case of ammonium ion, NH4 plus, look at here, in ammonium, three of them are covalent bonds, NH3, isn't it? These three are covalent bond. Here, okay, in this bond, nitrogen will share one electron, hydrogen will share one electron. Okay, this bond is formed by mutual sharing of electrons, therefore it is covalent bond. Here also, nitrogen will share one electron, hydrogen will share one electron. These are also formed, this bond is also formed by mutual sharing of electrons, therefore it's a covalent bond. Okay, yeah, in this bond also, nitrogen will share one electron, hydrogen will share one electron. This bond is formed by mutual sharing of electrons, therefore it is a covalent bond. But with other hydrogen atom, H plus ion, see, nitrogen has lone pair of electrons. Now, nitrogen will share both the lone pair of electrons with hydrogen. Okay, only nitrogen will share both the lone pair of electrons with hydrogen. Okay, so okay, the compound is formed like this, NH3. Okay, so here nitrogen will share both the lone pair of electrons with hydrogen and it forms a bond. And what is this bond called as? Coordinate bond. Here this hydrogen is not sharing an electron, it is not sharing any electron, only nitrogen is sharing both the electrons. So this bond is formed by sharing of electrons completely by what? Nitrogen, not by hydrogen. Such type of bond is called as a coordinate bond, and coordinate bond is usually indicated by an arrow mark. Okay, a coordinate bond or a dative bond is usually indicated by what? An arrow mark. So what is a coordinate bond? So if there are two combining atoms and only one combining atom will share the electrons, then a bond formed is called as a coordinate bond. You can also consider one more example. Okay, we can also consider one more example. Say for example, okay, the formation of ammonia, okay, and boron trifluoride adduct. Okay, adduct formation of ammonia and boron trifluoride adduct. How is this compound formed? In this adduct, okay, nitrogen, see all these are covalent bonds. In boron trifluoride also all these are covalent bonds, BF3. This is also covalent bond. Okay. So in this case, only nitrogen will share its lone pair of electrons with boron. Boron will not share any electrons with nitrogen. Only nitrogen will share the lone pair of electrons with boron, and it forms a bond. And what is this bond called as? It is called as dative bond. And how do you indicate a dative bond? Dative bond is indicated by what? Okay, an arrow mark. An arrow mark. Okay, simple. So if a bond is formed by sharing of electrons only by one of the combining atoms, then that bond is called as coordinate bond or a dative bond, or it is also called as electrovalent bond or coordinate bond. Electrovalent coordinate bond. Okay, is that simple, students? Yes. So now, before we understand hydrogen bond, the other aspects of hydrogen bond, let us understand, okay, the type of electron pairs. Okay, the type of electron pairs. Okay, yes. Before we understand about hydrogen bond, let us understand the type of what? Electron pairs. Electron pairs around central atom. The electron pairs around what? Central atom. Around central atom. Okay, look at here, students. If I consider ammonia, NH3, well, in this molecule, nitrogen is surrounded by two different types of electron pairs. Okay, in this molecule, the central atom nitrogen is surrounded by two different electron pairs, just like this. Look here, NH3 dot, two electrons. Okay, observe here. Nitrogen is surrounded by total 8 electrons according to octet rule. Nitrogen is surrounded by 8 electrons. 1, 2, 3, 4, 5, 6, 7 and 8, isn't it? So total nitrogen is surrounded by 8 electrons. Out of 8 electrons, look at here, this electron, this electron, this and this. So out of 8 electrons, 6 electrons are involved in bond formation, isn't it? Okay, out of 8 electrons, okay, 6 electrons are involved in bond formation, isn't it? Okay, they are involved in bond formation between nitrogen and hydrogen, bond formation between nitrogen and hydrogen, bond formation between nitrogen and hydrogen. So out of 8 electrons, 6 electrons are involved in bond formation. Well, those 6 electrons are called as, okay, yes, they are called as shared electrons. 6 electrons means 3 pair, isn't it? 6 electrons means 3 pair, correct? So those 3 pair of electrons, 1 pair, 2 pair, 3 pair. So these 3 pair of electrons are called as shared pair of electrons, or they are also called as bond pair of electrons. They are called as shared pair of electrons or bond pair of electrons. Are you able to understand my point? Out of 8 electrons around nitrogen, 6 electrons are involved in bond formation with, okay, between nitrogen and hydrogen, nitrogen and hydrogen, nitrogen and hydrogen. So 6 electrons means 3 pair, 1 pair, 2 pair, 3 pair. So these 3 pair of electrons which are involved in bond formation are called as shared pair of electrons or bond pair of electrons. And the remaining 2 electrons, they are not involved in any bond formation. They are not involved in bond formation. Out of 8, 6 are involved in bond formation and the 2 are not involved in bond formation. Now those 2 electrons means 1 pair. Is it correct? 2 electrons means 1 pair. Those 2 electrons are a pair of electrons which are not involved in bond formation. They are not involved in bond formation. They are not involved in bond formation. So those pair of electrons which are not involved in bond formation, they are called as lone pair of electrons. What are they called as? Lone pair of electrons. Okay, lone pair of electrons, or else they are also called as non-bonded electrons. Non-bonded electrons. So the pair of electrons which are involved in bond formation, they are called as shared pair of electrons or bond pair of electrons, and the pair of electrons which are not involved in bond formation are called as lone pair of electrons or non-bonded electrons. Non-bonded electrons. I will give you one more example to demonstrate this. Okay. If I consider water molecule, observe here. If I take water molecule, okay, is H2O. Sorry, okay. If I consider water molecule, okay, H2O, okay, H2O. Look at here, the central atom oxygen is surrounded by 8 electrons again. The central atom oxygen is surrounded by 8 electrons. 1, 2, 3, 4, 5, 6, 7 and 8, isn't it? The oxygen is surrounded, the central atom is surrounded by 8 electrons, so it satisfies octet rule, no doubt in it. But out of 8 electrons, 4 electrons, these 4 electrons, look at here, 1, 2, 3, 4. These 4 electrons are involved in bond formation. 4 electrons means 2 pair, is it correct? 2 pair of electrons are called as what? Okay, bonded electrons or bond pair of electrons, bond pair or shared pair of electrons. Shared pair of electrons. Whereas the remaining four electrons, like, okay, this electron, this and this, they are not involved in any bond formation. Again, 4 electrons means 2 pair, okay, they are not involved in any bond formation. Those electrons are called as lone pair or non-bonded pair of electrons. 2 pair, they are not involved in any bond formation, they are called as lone pair of electrons or non-bonded pair of electrons. Non-bonded pair of electrons. Non-bonded pair of electrons. Okay, hope you understood, students. Hope you understood. Yeah, we will study about bond pair and lone pair again in a theory called as valency shell electron pair repulsion theory, which we'll study in the upcoming videos, no doubt. So with this, students, we will move on to the next bond. Okay, next type of bond. What is the next type of bond called as? It is called as hydrogen bond. Okay, hydrogen bond. Okay, what do you mean by hydrogen bond, students? What is hydrogen bond? It is the bond formed between hydrogen atom and a more electronegative atom and a more electronegative atom like nitrogen, oxygen, fluorine. Okay, it is the bond formed between hydrogen atom and a more electronegative atoms like nitrogen, oxygen, fluorine. Well, this bond is called as what? Hydrogen bond. Okay, come again. What is hydrogen bond? It is the bond formed between hydrogen atom and more electronegative atoms like nitrogen, oxygen, fluorine. Well, if you consider hydrogen fluoride, students, if you consider hydrogen fluoride, okay, now look at between hydrogen fluoride molecules, what is going to happen? We know fluorine is more electronegative than hydrogen, isn't it? Fluorine is more electronegative than hydrogen, isn't it? So since fluorine is more electronegative than hydrogen, it will withdraw the shared pair of electrons towards itself. Okay, so fluorine will attract the shared pair of electrons towards itself, because fluorine is more electronegative than hydrogen. Okay, so since fluorine is more electronegative than hydrogen, what do you mean by electronegativity? The tendency to withdraw the shared pair of electrons, the tendency to attract the electrons. So fluorine has more tendency to attract the electrons, therefore fluorine will attract these electrons towards itself. When fluorine attracts the electrons towards itself, fluorine will get partial negative charge, hydrogen will get partial positive charge. Same thing happens here also. Fluorine will get partial negative charge, hydrogen will get partial positive charge. Okay, because here also fluorine is more electronegative than hydrogen. It withdraws the shared pair of electrons towards itself. So fluorine has partial negative, hydrogen has partial positive. Okay, fluorine has partial negative, hydrogen has partial positive. Fluorine has partial negative and hydrogen has partial positive. Now what is going to happen? The negative end of this molecule will attract the positive end of this molecule. The negative end of this molecule will attract the positive end of this molecule. Same, the negative end of this molecule will attract the positive end of this molecule. Am I correct? Look at here, there is a bond formation. A bond is formed between what and what? A bond is formed between hydrogen atom and a highly electronegative atom. A bond is formed between hydrogen atom and a highly electronegative atom. A bond is formed between hydrogen atom and a highly electronegative atom. Well, this bond is called as what? What is this bond called as? Hydrogen bond. It's a bond formed between hydrogen atom and a highly electronegative atom. It's a bond formed between a hydrogen atom and a highly electronegative atom. Well, this bond is called as hydrogen bond. Hydrogen bond. I can give you one more example. For example, in water molecules, how are water molecules associated together? Say water molecules, H2O. Okay, say I'll write it like this. Okay, look at here. So we know oxygen is more electronegative than hydrogen. So oxygen withdraws the pair of electrons towards itself. Hence oxygen gets partial negative, hydrogen gets partial positive. Here also oxygen is more electronegative than hydrogen. Oxygen withdraws the electrons towards itself. So oxygen gets partial negative, hydrogen gets partial positive. Same phenomena happens here also. Oxygen partial negative, hydrogen partial positive. Okay, oxygen partial negative, okay, hydrogen partial positive. Now the negative end of this molecule will attract the positive end of this molecule. The negative end of this molecule will attract the positive end of this molecule, isn't it? The negative end of this molecule will attract the positive end of this molecule. Here also, the negative end of this molecule will attract the positive end of this molecule. Look at there is a bond formation. A bond is formed between what and what? A bond is formed between hydrogen atom and a highly electronegative atom. A bond is formed between hydrogen atom and a highly electronegative atom. So this bond formed between hydrogen atom and a highly electronegative atom is called as what? Hydrogen bond. Hydrogen bond. Okay, clear? Yes. See, hydrogen bond depends upon two factors. Okay, hydrogen bond depends on two factors. Okay, depends upon two factors. What are the two factors on which hydrogen bond depends? The first factor is smaller the size okay, of electronegative atom, smaller the size of electronegative atom and higher the electronegativity, smaller the size and higher the electronegativity. Okay, look here, smaller the size and higher the electronegativity, okay, stronger will be the hydrogen bond, stronger will be the hydrogen bond. Are you able to understand? Okay, smaller the size and higher the electronegativity, stronger will be the hydrogen bond. Come again, what is it? Smaller the size and higher the electronegativity, stronger will be the hydrogen bond. I'll give you one example. See, okay, ammonia molecules, NH3, okay, ammonia molecules are also held by, see this, ammonia molecules, NH3 molecules, yeah, they're held by hydrogen, okay, hydrogen bond. Ammonia molecules, okay, are also held by hydrogen bond. Oxygen in water molecule also, water molecules are also held by hydrogen bonds, isn't it? Water molecules are also held by hydrogen bond, H2O. Observe this, okay. Yes, there is hydrogen bond here, there is hydrogen bond here, okay, there is hydrogen bond, there is hydrogen bond. Ammonia molecules are also held by hydrogen bond, water molecules are also held by hydrogen bond. But out of these two, which bond is stronger? Which hydrogen bond is stronger? Which hydrogen bond is stronger? We know oxygen is, okay, oxygen, look at here, oxygen is smaller than nitrogen, okay, and also oxygen is more electronegative than hydrogen, isn't it? Correct? Okay, oxygen is smaller than nitrogen and oxygen is more electronegative than nitrogen. Am I correct? So in ammonia molecules there is nitrogen and hydrogen, in water molecules there is oxygen and hydrogen. We know oxygen is, okay, smaller than nitrogen and also oxygen is more electronegative than nitrogen. The rule says smaller the size, higher the electronegativity, stronger will be the hydrogen bond. Therefore, can I conclude that, okay, a hydrogen bond is stronger in water molecules when compared to ammonia, isn't it? Hydrogen bond is stronger in water molecules when compared to ammonia molecules. Yes or no? Okay, please remember the rule. What is the rule? Smaller the size, higher the electronegativity, okay, higher the electronegativity, stronger will be the hydrogen bond. Okay, I'll give one more example to substantiate this. Okay, yes, what is that? Okay, see, we just now understood, okay, we just now understood that, okay, hydrogen fluoride molecules are held by what? Hydrogen bond. Hydrogen fluoride molecules are held by hydrogen bond. How about hydrogen chloride molecules? How about hydrogen chloride molecules? No, okay, there is no hydrogen bond in hydrogen chloride molecules. Okay, there is hydrogen bond only in hydrogen fluoride. Here there is hydrogen bond, but in this case there is no hydrogen bond. Can you please tell me why there is no hydrogen bond between HCl molecules and why there is, okay, hydrogen bond between hydrogen fluoride molecules? Yes, okay, we know as we go down the group, fluorine, chlorine, bromine, iodine, as we go down the group, atomic size increases, isn't it? As we go down the group, atomic size increases. Okay, that means chlorine is bigger than what? Fluorine. Okay, just now we understood, okay, hydrogen bond depends upon size and electronegativity. Okay, see, chlorine is bigger than fluorine and also chlorine is less electronegative than fluorine. Chlorine is bigger than fluorine and also chlorine is less electronegative than fluorine. Okay, but okay, for hydrogen bond size should be small electronegativity should be high. I told you the rule. Smaller the size and higher the electronegativity, stronger will be the hydrogen bond. Here, chlorine is a bigger atom and chlorine is less electronegative when compared to fluorine. That is why there is no hydrogen bond between HCl molecules, but there is hydrogen bond between hydrogen fluoride molecules, because fluorine is a small atom and fluorine is highly electronegative atom, isn't it? Fluorine is highly electronegative. It's a small atom. Smaller the size and higher the electronegativity, stronger will be the hydrogen bond. But there is no hydrogen bond between HCl molecules. HCl molecules. Okay, why there is no hydrogen bond between HCl molecules? Because chlorine is bigger in size and it is a less electronegative atom when compared to fluorine. Okay, any doubts with this? Okay, yes. Next. Well, students, hydrogen bond is of two types. It is called as intermolecular hydrogen bond. Okay, hydrogen bond is of two types. It is intermolecular hydrogen bonding and intramolecular hydrogen bonding. Okay, yes, intermolecular hydrogen bonding and intramolecular hydrogen bonding. Okay, please remember. Okay, so hydrogen bonds are of two types: intermolecular hydrogen bonding and intramolecular hydrogen bonding. What do you mean by intermolecular hydrogen bonding? If hydrogen bond is between two molecules, okay, of same type or different type, okay, if it is between two different molecules, if it is between two same molecules, or if it is between two different molecules, then that type of hydrogen bond is called as what? Intermolecular hydrogen bond. If the hydrogen bond is between two molecules of same type or two molecules of different types. Look here. Okay, what is the hydrogen bond called as between two hydrogen fluoride molecules? Here the hydrogen bond is present between two molecules of what? Hydrogen fluoride and hydrogen fluoride. Or what do you call the hydrogen bond that is present between an alcohol and water molecule? ROH and water, HOH. There is hydrogen bond, isn't it? Okay, so if the hydrogen bond is between two molecules, of same type or of different type, okay, this is alcohol, this is water. Here hydrogen fluoride. So if the hydrogen bond is formed between two molecules of same type or of different type, then it is called as intermolecular hydrogen bonding. What is it type called as? Intermolecular hydrogen bonding. But if the hydrogen bond is formed in the same molecule, if the hydrogen bond is formed in the same molecule, then it is called as intramolecular hydrogen bonding. If the hydrogen bond is formed in the same within the same molecule, then it is called as intramolecular hydrogen bonding. For example, orthonitrophenol. Look at here, orthonitrophenol. See this, N double bond O. This is one molecule. This is entirely one molecule. Within this molecule itself, there is hydrogen bond. Okay, so hydrogen bond is formed within the same molecule. Then that is called as what? Intramolecular hydrogen bonding. If the hydrogen bond is formed between two molecules of same type or of different type, intermolecule. Okay, intermolecular hydrogen bonding. If the hydrogen bond is formed within the molecule or within the same molecule, then it is called as intramolecular hydrogen bonding. Okay, see, okay, students, please understand this point. Okay, the compounds having intermolecular hydrogen bonding, will have high high melting point and boiling point than okay, intramolecular than compounds having intramolecular hydrogen bonding. Intramolecular, okay, hydrogen bonding. Okay, the compounds having intermolecular hydrogen bonding will have high melting point and boiling point than the compounds having intramolecular hydrogen bonding. Students, I'll substantiate this, okay, with an example in the next video. Thank you. Welcome back, students, to my video lecture 3 on chemical bonding and molecular structure. Students, I was talking about hydrogen bonding, okay, in my previous video, and I told you that there are two types of hydrogen bonding. One is intermolecular hydrogen bonding, the other one is intramolecular hydrogen bonding. What is intermolecular hydrogen bonding? The hydrogen bonding formed between the two molecules of the same type or of different type, then it is called as intermolecular hydrogen bonding. If the hydrogen bonding is formed within the same molecule, then it is called as intramolecular hydrogen bonding. So at the end, I have concluded with one sentence that, okay, the compounds having intermolecular hydrogen bonding will have, okay, high melting point and boiling point, then the compounds having, okay, intramolecular hydrogen bonding. Now I will explain this with an example in this video. Okay, yes, let us give an example for this. Okay, what is it? Compounds having intermolecular hydrogen bonding will have, okay, high melting point and boiling point than the compounds having intramolecular hydrogen bonding. Let us take orthonitrophenol and paranitrophenol. Okay, orthonitrophenol and paranitrophenol. What is it? Orthonitrophenol and paranitrophenol. See, orthonitrophenol, this involves, okay, intramolecular hydrogen bonding, whereas paranitrophenol involves intermolecular hydrogen bonding. So that means to say, the melting point and boiling point of paranitrophenol will be more than the melting point and boiling point of, okay, orthonitrophenol. Okay, why is this? Just look at here. Orthonitrophenol, it is something like this. Orthonitrophenol, okay, orthonitrophenol. These two are orthonitrophenol. So between in orthonitrophenol there will be intramolecular hydrogen bonding. We know what is intramolecular hydrogen bonding. What is intramolecular hydrogen bonding? Okay, the hydrogen bonding within the molecule is called as intramolecular. So here also there is hydrogen bonding which is called as intramolecular hydrogen bonding. Am I correct? Okay, yes. So how about paranitrophenol? Okay, just I'll write it here. Paranitrophenol, it goes like this. Paranitrophenol, just like this. Okay, see this? Paranitrophenol. Okay, so there is hydrogen bond between the molecules. That is intermolecular hydrogen bonding. This is intramolecular hydrogen bonding. So that is what I meant to say. So I want to melt this compound. If I have to melt this compound, there is, okay, the compound will easily melt. If I give little energy, if I supply minimum energy, the compound will melt because the molecules are not held by any bond. The two molecules are not held by any bond. But if I have to melt this compound, I have to supply more energy. Why I have to supply more energy? Because the two molecules are held by hydrogen bond. Therefore, in order to melt this compound or in order to boil this compound, I have to break this hydrogen bond, isn't it? I have to break this hydrogen bond in order to make this compound melt or to boil. Okay, that means I have to supply more energy. But here, minimum energy itself will make, the molecule melt or the molecule to evaporate or to boil, because the molecules are not held by hydrogen bonding. The molecules are not held by hydrogen bonding. There is intramolecular hydrogen bonding, there is intermolecular hydrogen bonding. So compounds having intermolecular hydrogen bonding should be supplied with more energy in order to break the hydrogen bond between the two molecules. Okay, but here, since there is no hydrogen bond between the two molecules, I have to supply less energy. Hence my conclusion is, now melting point and boiling point of compounds having intermolecular hydrogen bonding will be more than the melting point and boiling point of compounds having intramolecular hydrogen bonding. Okay, clear students? So that's all about hydrogen bond. I told you what is hydrogen bond, what are the factors that affect hydrogen bond, and what is intermolecular hydrogen bonding and what is intramolecular hydrogen bonding. Any doubts with this? Okay, that's great. Okay, next compound, next question and next concept, students. Now students, we have to learn something called as Lewis dot structure or Lewis dot structure. Lewis dot structure. Lewis dot structure. Okay, students, before we study Lewis dot structure, we should understand something called as formal charge. We should understand something called as formal charge. Okay, formal charge. So please remember the formula for formal charge. Okay, remember the formula for formal charge. Formal charge is equal to, total number of valence electrons minus total number of lone pair of electrons minus half of total number of shared pair of electrons. Are you getting it? So this is the formula. Please remember this formula, for formal charge. Formal charge is equal to total number of valence electrons minus total number of lone pair of electrons. We will get questions on this. We have got questions on this, previous year. Please remember the formula and try to learn how to calculate the formal charge. Formal charge is equal to total number of valence electrons minus total number of lone pair of electrons minus half of total number of shared pair of electrons. Are you able to remember this? Total number of valence electrons minus total number of lone pair of electrons minus half of total number of shared pair of electrons. I'll put it in a simple way. Can I write formal charge is equal to V minus L minus half of S. V minus L minus half of S. V, total number of valence electrons. L, total number of lone pair of electrons. S, total number of shared pair of electrons. Can you remember this formula? Yes. Formal charge is equal to V minus L minus half of S. Let us learn how to calculate the formal charge. I'll take certain molecules. I'll take some molecules here. Yes. For example, I'll take methane. One compound. Methane. CH4, methane. Let us calculate the formal charge on carbon and on all the hydrogens. and also, okay, I'll take ammonia, NH3. Let us calculate the formal charge on nitrogen and also on all hydrogen atoms. Let us calculate the formal charge on carbon and on all hydrogens. Let us calculate the formal charge on nitrogen and on all the hydrogens Okay, yeah, students. Okay, let us apply. Okay, let us calculate the formal charge on carbon first. Formal charge on carbon is equal to, okay, total number of valence electrons in carbon. Yes, remember, please be attentive. Carbon belongs to 14th group, isn't it? For 13th group, total number of valence electrons is 3. For 14th group, total number of valence electrons will be 4. For 15th group, total number of electrons will be 5. And for 16th group, total number of valence electrons will be 6. 17th group, total number of valence electrons will be 7. Boron family, carbon family, nitrogen family, oxygen family, halogen family. Okay, boron family, 13th group, total number of valence electrons 3. Carbon family, 14th group, total number of valence electrons is 5. Nitrogen family, 15th group, total number of valence electrons is 5. For carbon, 4. For oxygen family, 16th group, okay, total number of valence electrons will be 6. For halogen family, that is 17th group, total number of valence electrons will be 7. So carbon family means 14th group, so total number of valence electrons will be 4 minus. Is there any lone pair of electrons on carbon? No. Carbon is surrounded by 8 electrons. Carbon is surrounded by 8 electrons, and all the 8 electrons are bond pairs, that is shared pair. There are no lone pair of electrons. So number of lone pair of electrons is 0 minus half of. How many shared pair of electrons are there? 2, 4, 6, 8. So 8, correct? 2 ones are 2 fours are. 4 minus 4 is 0. So what is the formal charge on carbon? Formal charge on carbon is 0. Formal charge on carbon is going to be what? 0. How about the formal charge on hydrogen? Because here all the hydrogen atoms are same. So if I calculate the formal charge of one hydrogen, then the formal charge on all the hydrogen atoms will be same. You don't have to keep calculating the formal charge on all the hydrogen atoms. If you calculate the formal charge on any one of the hydrogen atoms, it is enough. Okay. So let us calculate the formal charge on hydrogen. Formal charge on hydrogen. We know hydrogen belongs to first group, so the total number of valence electrons is 1 minus. Any lone pair of electrons around hydrogen? No, there is no lone pair of electrons on hydrogen, so lone pair of electrons is 0 minus, okay, half of. Okay, hydrogen is surrounded by how many shared pairs? 2 shared pairs. Okay, so half of 2. 2 ones are, okay, 2, correct? 1 minus 1 is 0. Therefore the formal charge on this oxygen is also, on hydrogen is also 0. The formal charge on carbon is 0. The formal charge on oxygen is 0. Now, coming on to nitrogen and hydrogen in ammonia. Can we calculate the formal charge on nitrogen and hydrogen? Here also, okay, all the hydrogen atoms are same, isn't it? Okay, so if we calculate the formal charge on one oxygen, it is enough. It is enough. Okay, yes, let us calculate. Okay, yes, observe here the formal charge on nitrogen. Can we calculate formal charge on nitrogen? Yes, observe this. Formal charge on nitrogen is, okay, yes, nitrogen 15th group. So the total number of valence electrons is 5 minus. Look here, there are 2 lone pair of electrons, isn't it? There are 2 lone pair of electrons. So number of lone pair of electrons is 2 minus half of. Okay, how many shared pairs? 2. Okay, 2, 4, 6. 6 shared pairs, correct? 2 ones are, 2 threes are. 5 minus 2 is 3. 3 minus 3 is 0. So what is the formal charge on nitrogen? It's 0. Formal charge on nitrogen is 0. Let us calculate the formal charge on hydrogen. Okay, it is equal to, hydrogen belongs to first group, so total number of valence electron is 1 minus. Any lone pair of electrons on hydrogen? No, 0 minus half of. Okay, how many shared pair of electrons around nitrogen? 2. Half of 2. Okay, 2 ones are 2. 1 minus 1 is 0. So therefore the formal charge on hydrogen is also 0. Since all the hydrogen atoms are similar, so the formal charge on all the hydrogen atoms is also 0. 0. So what is the formal charge? What is the formula to calculate the formal charge? V minus L minus half of S. Total number of valence electrons minus total number of lone pair of electrons minus half of total number of shared pair of electrons. Okay. Last, I'll just take last example. Okay. To calculate the formal charge. Okay. Let us take up ozone molecule. Okay. Yeah, very famous question. They will keep asking you to calculate the formal charge on ozone. Okay, formal charge on, okay, I'll tell you what should be calculated. Ozone, O3. Look at the formula for ozone. O, okay, double bond O, single bond O, 1 lone pair, 2 lone pairs and 3 lone pairs. Okay, they will mark it as first oxygen, second oxygen and third oxygen. They'll ask you, calculate the formal charge on first oxygen, calculate the formal charge on second oxygen and calculate the formal charge on third oxygen. Okay, so we should, because all the 3 oxygen atoms are different here. All the 3 oxygen atoms are different. So you should calculate the formal charge on first oxygen, formal charge on second oxygen and formal charge on third oxygen. So let me calculate the formal charge on first oxygen. Observe here, oxygen means 16th group. So for 16th group, the number of valence electrons is 6 minus. How many lone pair of electrons on oxygen? 2, 4. 4 minus half of. How many shared pair of electrons? 1, 2, 3, 4. Half of 4. 2 ones are 2 twos are. 6 minus 4 is 2. 2 minus 2 is 0. Therefore, the formal charge on the first oxygen is 0. 0. Is that correct? Okay. Next, formal charge on second oxygen. Look here. Again, oxygen. Yeah, 16 group. 16 group is total number of valence electrons 6 minus. Okay, number of lone pair of electrons 1, 2 minus half of shared pair of electrons. Look here, 1, 2, 3, 4, 5, 6. Total number of shared pair of electrons is 6. Come on. Okay, 2 ones are 2 threes are. 6 minus 2 is 4. 4 minus 3 is 1. So plus 1. The formal charge on the second oxygen is, yeah, the formal charge on the second oxygen is plus 1. Plus 1. Are we clear? Next, last. Okay, yes. Let us calculate the formal charge on third oxygen. Look here. Yeah, 16th group, 6 electrons minus. Okay, lone pair of electrons 1, 2, 3, 4, 5, 6. So lone pair of electrons 6 minus half of shared pair of electrons 1, 2. Yes, 2. Correct. So 6 minus 6 is 2 ones are 2. 6 minus 6 is 1. 1 minus 1 is 0. Okay. Yes. What is the, okay. Okay. Yeah. 2, 4, 6. 6. Shared pair of electrons 2. Okay. Yes. 6 minus 6 is 0. Okay. 0. 0 minus 1 is minus 1. Okay. Therefore, the formal charge on the third oxygen is going to be minus 1. The formal charge on the third oxygen is minus 1. Are you able to understand? Okay. So what is the formula to calculate the formal charge? V minus L minus half. So students, if you know how to calculate the formal charge, then it is easy to write the electron dot structure. Okay. It is easy to write the electron dot structure. Okay. Yes. Formal charge is equal to V minus L minus half of S. Okay. Students, now let us learn how to write the Lewis dot structure. Okay, Lewis dot structure. Please learn this, because if you don't know how to write the Lewis dot structure, then everything is gone in chemical bonding and molecular structure. So please, okay, learn how to write the Lewis dot structure. There are different rules to write the Lewis dot structure. Let us understand the different rules by taking the examples itself. Okay, let us learn the different rules by taking the examples itself. I will tell you, okay, how to write the Lewis dot structure of ozone molecule. Okay, how to write the Lewis dot structure of ozone molecule. See this, the first rule says, okay, count the total number of valence electrons. Count the total number of valence electrons. Valence electrons. Okay, that is the first rule. Count the total number of valence electrons. There are 3 oxygen atoms. Okay, there are 3 oxygen atoms, and oxygen atom belongs to 16th group. Okay, 16th group, the valence electrons is 6. So 3 6 are 18, isn't it? So number of valence electrons. Number of valence electrons in O3 is equal to how much? 18. Okay, 6 oxygen belongs to 16th group. Okay, for 16th group the number of valence electron is 6. So 6 3s are 18. Now out of 3 oxygen atoms, you write, okay, one of the oxygen atom at the center, which is called a central atom, and distribute the other 2 oxygen atoms exactly, okay, equally at equal distance. Okay, distribute the other 2 oxygen atoms at an equal distance. Okay, you can write it like this, or you can write it in a straight way, because we are not worried about the structure. We are just worried about the formal charge. We are just worried about the formal charge and the Lewis dot structure. Okay, simple. Yes. So one of the oxygen atom is taken as central atom. The other 2 oxygen atoms are taken as the terminal atoms. Now join the central atom and the terminal atom, central atom and the terminal atom by single bond. Okay, join the central atom and the terminal atom by single bond. Central atom and terminal atom by single bond, like this, single bond. Clear? Now distribute these 18 valence electrons among the 3 oxygen atoms. Distribute these 18 electrons among the 3 oxygen atoms. Look here. Okay, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Okay, yes. Okay, 1 1 2 3 4 5 6 7 8, okay, 9 10 11 12, okay, 13 14 15 16 17 18. Okay, now just check. That is the second rule. Did you understand? We have completed 3 rules. The first rule is count the total number of valence electrons. The total number of valence electrons is 18. The second rule is, okay, write one of the oxygen atom at the center and distribute the other 2 oxygen atoms at equal distance. Second rule. Third rule says, okay, join the central atom and the terminal atom by single bond. Central atom and the terminal atom by single bond. Okay, third rule. Fourth rule, distribute this 18 electrons among the 3 oxygen atoms I have distributed. Okay, 1 2 3, okay, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. Now just check whether all the 3 oxygen atoms have attained octet structure or not. All the 3 atoms have attained octet structure or not. Well, look at this oxygen atom, 1 2 3 4 5 6 7 8. Well, this oxygen atom has attained octet structure. 1 2 3 4 5 6 7 8. This oxygen atom was also attained octet structure. But look at this oxygen atoms, 1 2 3 4 5 6. Well, this oxygen atom has not attained octet structure. If the central atom has not attained octet structure, use the lone pair of electrons from the terminal atom and make a double bond. Make a double bond. If the central atom has not attained octet structure, use the lone pair of electrons of the terminal atom and make a double bond. Make a double bond. Now check whether all the oxygen atoms have attained octet structure or not. 2 4 6 8. 2 4 6 8. Okay, sorry, 2, 4, 6, 8, 2, 4, 6, 8. Yes, all of them have attained octet structure. Very simple. Okay, by the way, we have calculated the formal charge also. This oxygen will have +1 charge and this oxygen will have -1 charge. Well, this is the Lewis dot structure of ozone molecule. Lewis dot structure of ozone molecule. Any doubts? The first rule, count the total number of valence electrons. Second rule, okay, write one of the oxygen atom at the center and the other two oxygen atoms at equal distance. The third rule, join the central atom and the terminal atoms by single bond. Fourth rule, distribute the valence electrons among the central atom and the terminal atom. Fifth rule, check the octet structure. Sixth rule, if the octet structure is not complete, then complete the octet structure by drawing a double bond using the lone pair of electrons from the terminal atom. Okay, yes, and write the formal charge. This is the Lewis dot structure of ozone molecule. Ozone molecule. I hope you understood, students. Any doubts with this? Okay. Yes. So far, student, tomorrow, in the next class, in the next video, we will learn how to write, very important, students, we will learn how to write the Lewis dot structure of ammonium ion. We will learn how to write the Lewis dot structure of carbonate ion. We will learn how to write the Lewis dot structure of SO4 2 minus, okay, and PO4 3 minus. PO4 3 minus. Okay, we will learn how to write the Lewis dot structure of ammonium, carbonate, sulfate, and phosphate. Okay, is that simple? So, students, so far we have discussed. Okay, instead of that, can I just finish the writing the Lewis dot structure of ammonium ion? Okay, just listen. Let us take ammonium ion. Now, what is the rule? Count the total number of valence electrons. Nitrogen, 15th group. So 5 electrons. Is it? 5. Okay, hydrogen, first group, 1 electron. 1 into 4 is 4. Okay, total number of valence electron is 9. But see, students, there is a positive charge. If there is a positive charge, we should subtract that charge. If there is a positive charge, we should subtract that charge. Okay, if there is one positive charge, means subtract 1. That means the total number of valence electrons is going to be 8 now. The total number of valence electron is going to be 8. Are you getting my point? Simple. Now, write nitrogen atom, which is the central atom at the center, and hydrogen atom is equally distributed around nitrogen. Sorry, hydrogen atoms is equally distributed around nitrogen. No doubt in it. Okay. Second rule over. The third rule says join the central atom and the terminal atom by single bond, single bond, single bond, and single bond. Okay, that's correct. Next, okay, what is the third rule? Distribute the valence electrons around the nitrogen and hydrogen. Okay, can we distribute? Yes, 1, 2, 3, 4, 5, 6, 7, 8. Now check whether all the atoms have attained octet structure. Be careful, for hydrogen we cannot have octet structure, we can have only doublet structure. So does hydrogen has doublet structure? Yes. 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 How about nitrogen? Does nitrogen has octet structure? Look here, 1, 2, 3, 4, 5, 6, 7, and 8. Yes. The octet structure of nitrogen is complete, and also the octet structure of hydrogen is complete. Yes. So this is the Lewis dot structure of ammonium ion. A point to be noted here, if there is a positive charge, you should subtract that positive charge with the total number of valence electron. We got the total number of valence electrons to be 9, so you will subtract one positive charge. So the total number of valence electrons is going to be 8. So in the next class, I'll be talking about the Lewis dot structure of carbonate, the Lewis dot structure of sulfate, and the Lewis dot structure of phosphate. So students, so far we have discussed about octet rule, limitations of octet rule, okay, ionic bond, factors affecting the formation of ionic bond, characteristics of ionic bond, covalent bond, characteristics of covalent bond, factors affecting the formation of covalent bond, Fargen's rule, coordinate bond, hydrogen bond, factors affecting hydrogen bond, types of hydrogen bond. Okay, yes, we learned how to calculate the formal charge, and we are learning how to draw the Lewis dot structure. Okay, students, we will continue with Lewis dot structure in the next video. Okay, yes, thank you so much.